Everyone. All right, so this is for section 7.3, and this is on the topic of separable differential equations. And for this, if you remember back from section 7.1, I explained that there are generally three techniques for solving a differential equation. And this goes with the analytical technique. This is the analytical technique that we learn in AP Calculus. There are other analytical techniques that are beyond the scope of the course, so we're not going to obviously cover those. But for our purposes, this is the one technique that we have to use in order to solve differential equations. I guess we can say one advanced technique, because finding an antiderivative technically is solving a differential equation, but it's trivial, and it actually would fall under this class here as trivial examples of this. And we'll look at one of those in just a moment. So, what is a separable differential equation? I just took this from our textbook, and so this is, as it says here, a separable differential equation is a first-order differential equation. Um, don't even worry about what that is, because that's all you're going to see here for our class. And it's a first order differential equation that can be factored into a function of x multiplied by a function of y. And if we could rewrite the differential equation algebraically to be in that form, then it is separable, and then we'll go apply the techniques that I'm going to demonstrate for you in just a moment. Now, what do I mean by a function of x multiplied by a function of y? Well, if I can rewrite it as dy over dx is equal to some function of x times some function of y. I mean, that's what a general form of this would look like. But one thing you have to keep in mind is that really division and multiplication are essentially the same operation. When we divide, we're really just multiplying by the reciprocal of something. And so there are other forms that would match this pattern that we have to be aware of, that we don't want to limit ourselves to only seeing it one way. So it could be the function of x divided by the function of y, which again, because division is just multiplication by the reciprocal, this is still just a function of x multiplied by a function of y. And so that still matches our definition. Or we could take the reciprocal form of that expression as well and have the function of y in the numerator and divide by the function of x. And so, again, we could think of this as f of y times 1 over g of x. And that, again, is a function of x. 1 over g of x is still a function of x times a function of y. Now, note in these two second forms here, I don't want f of y to be 0. I never want to have division by 0. And I don't want g of x to be equal to 0 either. So, but you guys all know that. So we'll just make it explicit here. So just to keep things simple, I'm going to pull the second form out really quickly and give you a general sketch of how this is going to go, and then we'll start applying it to some specific examples. So if I had the differential equation dy over dx is equal to g of x divided by f of y, then the process of separable differential equations is this. We're going to get everything that involves y to one side of the equal sign, and everything that involves x to the other side of the equal sign, and then we'll work on taking antiderivatives from there. Now, when I say the phrase, get all the y's on one side or get all the x's on the other side, you have to do this with correct algebra. So don't break any algebraic rules to do this. Do this with legitimate algebraic properties, principles, to get from one correct form of an equation to another, and then you'll be good to go. In this example here, now I've talked about this briefly at other times, but the expression here, dy over dx, is really not a fraction. It's called a differential operator. It's really d over dx, and then we're evaluating d over dx of y. But mathematicians, even though they make rules like this where they say that's not a fraction, don't treat it like a fraction, they like to break their own rules. And so they actually do treat this as a fraction, at least temporarily, for certain instances, and we've done that a little bit when we did our substitution. Instead of when we let u equal some expression, we didn't write du over dx in the next step consistently. We would write du is equal to something times dx. Again, breaking the rule that that's not a fraction. They treated it like a fraction then, and we're going to treat it like a fraction now, even though technically it's not. So in order to rewrite this, so all the x's are on one side, the right side in this case, and all the y's are on the left side, we're going to just do what we would, call in, fifth grade math or sixth grade math, whenever that came up, is cross multiply. And so if I were to cross multiply here, I get f of y dy equal to g of x dx. And all the y's are on one side, all the x's are on the other. That's our separation step. And then we're going to take antiderivatives of both sides. So we're going to take the antiderivative of fy dy, antiderivative of gx dx. And then from there, we'll continue to solve the problem. We'll find those antiderivatives and then solve for y, and sometimes find a particular solution to the differential equation. So that's the process. Let's actually take a look at some examples on how this works. So for example number one, we're going to do a essentially trivial example here, but we want to just look at the mechanics of this a little bit and talk about the solution set, and then we'll build up from there. So again, we'll start simple, crawl before we can walk, before we can run. And so we're going to solve the separable differential equation, dy over dx equals 2x. Again, this is trivial because we really don't need the concept of a separable differential equation. We solved this back when we thought about just antiderivatives initially at the end of chapter 4. And so we have the solution to this. But the point is to see how this works so that we can then apply the technique to more complicated examples later. Okay. Now you might think, well, on the right-hand side, I have 2x over there, but that's not a function of x times a function of y. And technically you don't see the y there, but there is a function of y that's there. You could just think of it as, y to the 0 power, if you will, if you want. Okay. And y to the 0 is 1, provided y itself is not 0. And so, if you want to think of it like that for this, that's fine. But we can even ignore that additional expression added or multiplied into that right hand side as a factor. We do have y over here in the numerator of this differential operator, and so there is a y in the equation. There's just no y's on the right hand side. So we're still okay here. We're still gonna. This still. Is consistent with what we're trying to do. Okay, so I'm going to separate my variables, quote unquote, cross multiply, if you want to think about it that way. And when I do that, I'm going to get dy left alone on the left-hand side equal to 2x dx on the right-hand side. So I've separated my variables. Put all the y's on one side, all the x's on the other. Legitimate mathematics to get there. Now I'm going to take the antiderivative of both sides. So I'm going to integrate dy with respect to y. I'll talk about that more in just a moment, and then integrate 2x with respect to x. Really, on the left-hand side here, I'm not integrating dy with respect to y. I'm really integrating 1 with respect to y. There's an invisible 1 on the out in front here. And so when you're thinking about finding the antiderivative of the left-hand side, again, you're taking the antiderivative of 1. And what expression in terms of y has a derivative of 1? Well, that's just y. So on the left-hand side, we're going to get y. On the right-hand side, the antiderivative of 2x with respect to x, of course, is just x squared plus constant. Now, you might be thinking to yourself, well, we put a constant on the right-hand side. How come we didn't put a constant on the left-hand side? And I think I've talked about this before, but just in case I didn't or you don't remember, let's just do a little bit of side work over here. I could have, if I wanted to, had included a constant of integration on the left-hand side, but I would have to distinguish it from the constant of integration on the right-hand side. So I'd have to use two different letters, not in use already in the problem, or subscript like I did here. And that's still a correct solution to this. But we know that algebraically I could just do a little bit of arithmetic here. And whoops, that one should be C sub 1. And solve this expression here, or this equation, to look like y equals x squared plus c sub 2 minus c sub 1, whatever that is. But whatever that is, that's just some constant, because c sub 2 is a constant, c sub 1 is a constant. Their difference is going to be some constant, some number. And so I'm just going to call that number c, and then we're right back to what we have over here. So I only need one constant of integration to account for all the constants of all the antiderivatives that we're taking in doing this process here. Okay, so just one constant is needed. Okay, so we get our solution here. So this is the framework that we're going to be doing this. Okay, we have our separable differential equation that we start with. We'll separate all the y's to one side, all the x's to the other using algebra. And then we're going to take the antiderivative of both sides. And then we can't forget our constant of integration. The nice thing about this one is we're already solved for y. That's not going to happen all the time. And so we might have to do a little bit of algebra at the end of the problem to solve for y, if the problem asks us to. Now remember, the solution here gives us a family of curves. That's something we have talked about before. And so let's go take a look, just as a reminder. So here are some members of the family of curves for several different values of c. And so, of course, there'd be an infinite number here because that constant c could be any real number. And the nice thing here is all these curves are, vertical shifts from each other. So if I zoom out a little bit here, we could fill up if I wanted to type in more values that c could be, and we could get a whole, series of these, or a larger collection of these curves in the picture here. Now, one thing we're going to have to do often with separable differential equations is we're going to be asked to find a particular member of the family, okay? So I got these, members of the families right here, these 7 curves, but what if I wanted to find the one member of the family that goes through the point 2, 0? Well, none of these members that I have up there do. So what would I do? In case you don't remember, let's go back and take a look. So if the curve has to go through the point 2, 0, then I'm going to plug in 0 for y and 2 for x and solve for c. So if I plug in 0 for y, I get, of course, 0 is equal to 2 squared, which is 4, plus c. So that means c would have to be equal to negative 4. And so we would get y is equal to x squared minus 4 as the particular solution that goes through 2, 0, the particular member of the family that goes through 2, 0. So let's go back to the graph for just a moment and take a look. There it is in green. Here you can see the equation, but you can see that curve is the one that goes through there. So we're going to need to be able to do that oftentimes, most of the time. So you want to be comfortable with that process of solving for the particular value of c. All right, let's solve the differential equation for y equals f of x, given that y of 1 is equal to 2. All right, so here we're looking for a particular solution because they gave us this extra information here, y of 1 equals 2, which means we're trying to find a particular solution. This is one way that the question could be asked. Also notice that it says to solve for y equals f of x, which means we're not just getting an equation that is a solution. We have to solve that equation for y. So if it's not already, like our first example up here, this one was already in terms of y, so I didn't have to do anything else to it, okay? When we got it, it was y equals x squared plus c. So I didn't have to solve for y. Here, I have to make sure I solve for y, even if it's not already in terms of y, because that's what the question is asking. I would love for you to pause the video and to go see how far you can get without me. All right, here I go. So I'm going to separate the variables. We're going to multiply both sides by y, multiply both sides by dx, if you will. So we'll get y dy is equal to x dx. And then I'm going to integrate both sides. So definite integral, or rather the indefinite integral of y with respect to y is going to be equal to the indefinite integral of x with respect to x. And if I Take an antiderivative over here, you get 1 half y squared. Take an antiderivative over here, you get 1 half x squared plus c. Ladies and gentlemen, you cannot forget that plus c. In this type, especially in this type of example, on the AP exam, this could be a 4 or 5 point question on the some part of the free response portion of the AP exam, where 1 point is for each antiderivative. Here, because they're really simple and they're actually the same, they might only give 1 point total for both. But sometimes, if they're different expressions on both sides, you get a point for the antiderivative of y, you'll get the point for the antiderivative of x, plus a point for the plus c, plus a point for using the initial condition, and then a point for solving for y. So this could be a very valuable question. And if you get sloppy with it and you forget the plus c, you're really going to lose a chance to get a lot of points. And it's really easy to get those points because you put the plus c, that's a point. Then you use the one, y1 equals 2, plug in 1 for x, 2 for y, solve, and then solve for y. There's a lot of points to be had here that are not that hard to get, provided you just do what I'm instructing you to do. All right. Anyway, let's continue here. Now, I did say that we're going to have to solve for y. My advice to you, though, I'm telling you right now, don't solve for y yet. Solve for c first, then solve for y after you put that value of c into it. Generally speaking, algebraically, it's going to be a little bit easier for all of you to accomplish it that way. And so that's my advice. So at the point 1, 2, because they said y of 1 is equal to 2, we're going to get, so I'm going to plug in 2 for y and 1 for x. And I'll solve this for c. So over here we get 2. Over here it looks like we get a half plus c. So c is going to be 2 minus a half, 1.5, or 3 halves if you want to use the fractional form, which I do. So now I'll go plug that back in. 1 half y squared is equal to 1 half x squared plus 3 halves. And now all we have to do is solve for y. Okay, so let's see. Let's multiply by 2 first to clear the halves, all the fractions. Now, to solve for y, and they love to do this on the AP exam, so this is good practice for you in your work right now. We have to take square root, but you have to remember algebraically that when we impose a square root, there could be a positive root or a negative root as the solution. So here I'm going to indicate my understanding of that by putting the plus or minus in front. And now we have to choose, okay? Plus or minus the square root, we're going to get something that's not a function. So if you stop right there, your answer is not complete, not correct, and you will not get full credit. Now, the only thing we have to realize is whichever one we choose, because we have two choices right now, we have either y is equal to the positive root, x squared plus 3, or I'm putting a little extra writing into this right now because I want to make sure you understand my explanation. Those are the two things that I'm considering. Now, remember, the curve has to go through the point 1, 2. The solution does. Which one of these is going to go through 1, 2? Well, you could just check. Plug in 1 for x and see which one gives you 2. Okay? If you plug it into this one over here, hopefully you can see without doing much work that you're going to get a negative 2 as the output. So that one's not our solution here. This is the one that we're going to have to throw out because it doesn't hit the curve, hit the point. That curve doesn't hit the point 1, 2. Okay, so because the curve has to go through 1, 2, the solution has to be the positive root for this example. But you should just double check this all the time. You should always take that point and make sure when you plug in the x coordinate, you get that y coordinate. That verifies that you have the correct solution to this curve. All right. Hopefully you're able to get that. All right, so here's example 3. I'm not going to rewrite the statement every single time, but you're solving this differential equation for a particular solution, y equals f of x, and y of 4 is equal to 3. So unless I state otherwise, either verbally or I write it differently, that's what we're doing. Even if I forget, that's what we're doing here. This is very similar, so hopefully with your understanding of the previous example, you can solve this on your own. So please pause and give it a shot. All right, so again, we're going to separate the variables. So y dy is going to be equal to negative x dx. Now you have a choice, and it really is your choice, and the steps might look a little different along the way if you do it the other way. But where that negative goes is your choice. Okay, I'm going to leave it with the x. I could have brought it over with the y. Algebraically, they're equivalent. And again, the steps that I use along the way to solve this might bring this into, they might look a little different along the way. But that's, again, those are trivial little things. Maybe you should try it both ways and see how they're the same and how they're different, and that you can arrive at the same answer either way. But anyways, I've separated the variables. So let's take antiderivatives. Notice how I put this step separately. On the AP exam, you want to make sure that the readers of your work know what you're doing the entire time and know that you know the steps in the solution. So explaining yourself with enough detail is important. So they're not going to give you the benefit of the doubt. They want to make sure that they see that you have an understanding. So you are demonstrating your understanding of separable differential equations by separating the variables and then showing that you're taking the antiderivative of both sides. And it's good to, in my opinion, show those separately so that they could see clearly what your intentions are for this along the way. All right, so 1/2 y squared is going to be equal to negative 1/2 x squared plus a constant. And again, we're given the 0.4 comma 3, so we're going to plug that in here to solve for c. And with this, what do we get? 9/2 is equal to negative 8 plus c. I guess I could leave that because I already got the 9/2. I could leave this as negative 16/2. So I already have that common denominator there. So that ends up with being 25/2 when I add the negative 16/2 to both sides. That's going to be c. And so I'll go plug that back in up to here, this equation. 1/2 y squared is equal to negative 1/2 x squared plus 25/2. Clear the fractions. Negative x plus 25. And for this, solve. Again, take it to square root. So we get our plus or minus. Let's go 20. I'm going to reverse this a little bit. And then I'm going to talk about the solutions here for those who maybe don't quite notice what's going on in this example. So we get y is equal to plus or minus root 25 minus x squared. So remember, we're choosing one of the two solutions. And since, I'll write it this way, since 4, 3 is on the solution curve, it's supposed to say curve, but it really didn't. Okay, on the solution curve, y is going to equal the positive root here, 25 minus x squared. Since y of 4 is going to be the square root of 25 minus 16, 4 squared, which is the square root of 9, which is just 3. So here's our answer right here. Now, maybe you recognize what this this function would look like if we were to graph it. Hopefully you do. This is the upper half of a circle, or this is a semicircle, the top half of a circle centered at the origin with a radius of 5. The previous step before solving for y up here, this step, the negative part would be the lower half of the circle, the bottom semicircle. And so the solution to this is just a semicircle, okay? Either the upper half or the lower half, depending on where the point has to go through. And since the point is a positive y coordinate, then we would have the upper half of the circle. And so if it had a negative y coordinate, we'd want the lower half for that one. So hopefully you're able to come up with that on your own without any help. Okay, again, so we're going to solve this differential equation for y equals f of x. And so we're looking for a function. That's partly what that notation in the instructions are telling you. So that's why we're not choosing, like in the previous example, the entire circle, because it's not a function. We're looking for a function that is the solution to the differential equation. And y of 2 is equal to 2. So we're looking for the particular one that hits the point 2, 2. Now, although this looks similar to the last two, as we have, a ratio, in the previous two it was x over y, one of them being negative. Here we have y over x. And so do we get similar types of solutions? Well, let's find out. Pause the video, go work it out, and then come back and see what I end up with. So again, when we're separating the variables here, we have to use correct algebraic processes. And so when I use the correct algebraic processes, I'm going to move this y over by dividing both sides by y, or multiplying by 1 over y, which is the way I prefer to write it. So I'm going to end up with 1 over y dy is equal to 1 over x dx. Okay. This one here is going to have a different solution and different things that we're going to have to account for. But there's our separation of variables. So let's take our antiderivatives, or note our antiderivatives, so our reader understands what we're doing through this process. The antiderivative of 1 over y with respect to y, hopefully you have that locked and loaded from your experience. It's the natural log of the absolute value of y. Make sure you have that absolute value symbol there. Similarly, over here, we're going to end up with the natural log of the absolute value of x, and of course, plus a constant. Let's go ahead and get that constant found by using the point 2 comma 2. I write in that point there so that my reader knows where our things are coming from. Okay. Now it's nice to include sentences also with things, but I'm talking to you, so we know the curve has to go through 2, 2. You could put it, you could put something like, since 2, 2 is on the curve, and then from there we're plugging in 2. The absolute value of 2 is still 2, so I can actually drop the absolute value symbols on this part of the expression. So well, that's kind of nice. That tells me that c in this case happens to be 0. Okay, and so since c is 0, that means I got the natural log of the absolute value of y is equal to the natural log of the absolute value of x. All right, so what does this tell us? Well, remember, we got to solve for y, so I have to undo the natural log. Hopefully you remember how to undo a natural log. We're going to exponentiate both sides, base e, like this. And that means the e and the natural log, they're going to cancel with each other. And don't be lazy. We still have an absolute value of y left on this side. And similarly, we're going to have the absolute value of x on this side. All right, so what does that tell us? Well, when I drop the absolute value symbol, or when I do it, remember the output of the absolute value symbol either takes the input and keeps it the same, which we would note with a plus, or makes it the opposite, which we would denote with a minus. So I can put a plus or minus y here to indicate what's going on. And then I can put a plus or minus x over here, but it's a little redundant to put it in both places. So what we do is we only put it in one. We'll put it on one side only as we're getting rid of this. Okay, so I either get the solution y is equal to x, or y is equal to negative x in that case here. But remember, the curve has to hit the point 2 comma 2, so we don't want this one over here. The answer to our problem is going to be y is equal to x. All right, so that's enough for this video. I'm going to do some more examples in the next video. Go study.